Hello geometry students, welcome to this video on the converse of the Pythagorean theorem, another way to ruin triangles for you. Actually, I'm just kidding. This one is actually kind of neat because we can use the Pythagorean theorem in sort of a unique and creative way to be able to tell whether a triangle is obtuse or acute. Now, here's another thing I'm going to tell you. Do not believe your lying eyes when you look at a diagram that shows a picture of a triangle. Maybe, for example, this picture of a triangle here is obtuse. It sure does look obtuse, but it would be great to be able to prove that it's obtuse. And that's what today is all about. We're going to talk about how you can prove that a triangle is right using the converse of the Pythagorean theorem. Or you can prove that a triangle is acute or obtuse using a slight adjustment of the Pythagorean theorem called the Pythagorean inequality theorem. This one only applies to identifying right triangles. Okay, this one applies to any triangle. So we're going to generalize the Pythagorean theorem today to work with any triangle. It's not going to help us calculate the sides, but what it will do is tell us whether or not the triangle is acute or whether it's obtuse. Okay, so let's take a look. Remember, the Pythagorean theorem really truly states not just a squared plus b squared equals c squared. There's an if-then statement there. And the if-then statement is if a triangle is a right triangle, then a squared plus b squared equals c squared. And really, it's more than the squares of the two shorter sides are equal to the sum of the squares of the two shorter sides is equal to the square of the longest side. That's the Pythagorean theorem. For the converse, we flip around the hypothesis and the conclusion. Okay, remember our hypothesis before was if a triangle is a right triangle. Now it's if the sum of the squares of the two shorter sides of a right triangle is equal to the square of the longest side, that's a squared plus b squared equals c squared. If that's true, if a squared plus b squared does in fact equal c squared, then the triangle is a right triangle. So this can help us identify right triangles, but it's limited in that if we say something's not a right triangle because a squared plus b squared doesn't equal c squared, Theorem 33.1 doesn't give us much help. Theorem 33.2, though, tells us, okay, if a squared and b squared is not equal to c squared, let's take a look at what it is. Is it less than c squared? Because if it's less than c squared, that means the triangle is obtuse. These two side lengths are shorter than they would have needed to be in order to make up the size of c squared. So the triangle is obtuse. If these two side lengths squared, when you add them together, come out to a number that's greater than c squared, then the triangle is acute. Now there is something here that seems a little counterintuitive, and I want to make sure that I talk about it so that you understand it, because your brain wants to think one thing by default on this, and the thing that you think by default probably is not correct. Okay, and this is what it is. You tend to think of acute triangles as small triangles. So hey, because an acute triangle is a small triangle, shouldn't it be true that the sum of a squared plus b squared for an acute triangle is less than the c squared value? And shouldn't for an obtuse triangle, since they're big angle triangles, shouldn't a squared plus b squared be greater than c squared? Well, you'll notice it's just the opposite in the Pythagorean theorem proof. And I'm just going to borrow two triangles from down here. One of them we're going to use with the c that is intended for us to use, this long side. Okay, this we're going to assume is an obtuse triangle, even though we have to actually prove that it's obtuse later. Up here, we're going to assume that this is an acute triangle. But I'm going to use this in a little bit of a non-standard way just to help you make sense of it. So we're going to pretend that 14 is side C, and that 8 and 15 are the legs, and then 14 is the side that we're going to assume is supposed to be the hypotenuse. So we're using it that way just for illustrative purposes. Most of the time when you do this, you're going to actually have to use the longest side as side C, but it's going to be okay on this one. I just need it to prove a point. All right, so let's take a look And actually, I could use a triangle to prove 3 points. All right, but anyway, let's take a look at this triangle down here. Notice that I have two legs that are pretty short and a hypotenuse, quote unquote. It's not really a hypotenuse, it's not a right triangle, but it's like the longest side of the triangle is really stretched out. These legs have really stretched out the length of this longest side across from the obtuse angle. And because this side gets really stretched out, when you're dealing with the hypotenuse, the longest side of a non-right triangle that's obtuse, this is just going to be really big. It's the square of this longest side is going to have a really, really big value compared to the squares of the two legs. Okay, so one of the questions you should ask yourself is, which relationship are we going to have to put more ink on paper to draw the legs compared to the amount of ink we have to put on paper to draw the hypotenuse? And these legs down here, they do take quite a bit of ink, more than the longest side, right? We'd have to have more than the longest side. But look at how much ink I have to put down to draw this hypotenuse, to stretch it all the way out from one end to the other. Now, for contrast, take a look at this. If our legs form an acute angle like this, my hypotenuse doesn't require as much ink to draw anymore, because it's going to be really short compared to the two legs, especially when I compare it to what happened over here. Okay, so we're going to say that the two shorter sides, we'll call them the legs. We're going to kind of treat this like it's a right triangle, even though it's not. So these two sides here are going to make this acute angle, which actually compresses the size of the hypotenuse, quote unquote hypotenuse, right? And because this hypotenuse is smaller than it otherwise would be if it was stretched out obtuse, when I square it, it's going to have a smaller value compared to the sum of the squares of the other two sides. And that's what we're dealing with when we are using the Pythagorean inequality theorem. So notice that a squared plus b squared for an obtuse triangle is going to be shorter than c squared, because c squared is really stretched out in an obtuse triangle. And that's what I want you to think about. That's what's going to help you keep the Pythagorean inequality theorem straight, because your brain is going to want to fight you on this, and it's going to want to make you say, okay, the one that's got the smaller legs is going to be the one that's acute. But that's just not true. You have to think about instead how stretched out the hypotenuse is. That's how stretched out is this side C. If side C is so big and so stretched out that it's bigger than a squared plus b squared, then the triangle is obtuse because it is a really stretched out hypotenuse, quote unquote, like longest side. And if the longest side is short, the square of the longest side is shorter than a squared plus b squared, this is really compressed a longest side, which means the triangle is acute. That's the best way to think about that one. Okay.